You know, our entire digital world, everything from that movie you're streaming to the video calls you're on, it's all just pulses of light traveling through glass threads thinner than a human hair. But keeping that light signal perfect is a huge challenge. So today, let's dive into the hidden world of fiber optics and explore the spectrum of colors that keeps our internet up and running.
I mean, really think about that for a second. We're talking about a tiny microscopic crack, or maybe a slight bend, or a bad connection somewhere in a cable that could be stretching from one city to the next. A flaw like that could bring down an entire network. It's basically like finding one single broken needle in a haystack that's the size of a highway. So how on earth do technicians do it?
Well, they do it with a really brilliant piece of technology. It's kind of like a radar system, but instead of sending out radio waves, it uses the very thing it's testing, light itself. This incredible device, the hero of our story, is called the OTDR.
So here's the gist. An OTDR zaps a quick, powerful pulse of light down the fiber. As that light travels, any little imperfection, a splice, a bend, a break, reflects a tiny bit of that light back to the device. By measuring exactly how long it takes for those reflections to come back and how strong they are, the OTDR can map out the fiber and pinpoint the exact location and even the nature of a fault. Pretty smart, right?
Okay, but this is where it gets really interesting. You might be thinking, all right, you send a pulse of light, you get a reflection, job done. But it's not that simple. To get the full story of a fiber's health, you actually need to test it with a whole spectrum of light. To understand why, we first need to meet the two great enemies of any light signal. So every single pulse of light that's zipping down a fiber optic cable, it's facing two major threats that are trying to degrade it into nothing. These are attenuation and dispersion. You can think of them as the villains constantly trying to sabotage your data.
In the simplest terms, attenuation is the light pulse getting fainter and fainter, weaker and harder to detect. Dispersion, on the other hand, is the pulse getting blurry and spreading out, making it really hard to read. And trust me, both of them can be catastrophic for sending data.
Now, what's really fascinating is that this signal loss, this attenuation, it's not the same for all colors or wavelengths of light. And this graph shows us why. See the big dips in the curve? Those are the sweet spots. For example, down here around 1550 nanometers, the loss is super low. That means light at that wavelength can travel for enormous distances. But in other areas, the light gets absorbed or scattered and just fades out way more quickly.
Now, dispersion is a bit more subtle, but it's just as damaging. Imagine a perfectly sharp, clean pulse of light representing a single bit of data. Dispersion basically smears that pulse out over time. And if it gets too smeared, it starts to overlap with the next pulse. And all of a sudden, your ones and zeros become a totally indecipherable mess.
So why does this smearing happen? Well, there are a couple of main culprits. In what's called multi-mode fiber, it's because light can take different paths, almost like cars in different lanes on a highway. But in the single-mode fiber that makes up the internet's backbone, the main troublemaker is chromatic dispersion. This is where different colors within the light pulse actually travel at slightly different speeds.
But here's the magic trick. Engineers discovered that at one specific wavelength, 1310 nanometers, two different types of dispersion, one caused by the glass material itself and the other by how the light is guided down the fiber, they have opposite effects. And at this exact wavelength, they perfectly cancel each other out. This creates a zero dispersion point. At this precise color, the light pulse stays incredibly sharp and clear. It's an amazing bit of physics. So, what do we have? We've got some wavelengths that travel farther and others that stay sharper. And technicians can use these unique properties to their advantage. Each different wavelength becomes like a specialized detective, perfectly suited for finding a specific kind of clue or problem in the fiber. This table here really shows how it all comes together. If you use 1310 nanometers with its near-zero dispersion, the OTDR gets the absolute clearest picture of things like connection points and sharp bends. But at 1550 nanometers, that's the wavelength where the light travels the farthest, making it perfect for measuring those super long-haul cables and detecting subtle stress. And then you have 1625 nanometers. It's extra sensitive to bending, which makes it perfect for a very special task we'll get to in just a minute. You know, for a long time, there was a whole section of this light spectrum that was completely unusable. It was like a dead zone, and it was caused by a kind of ghost lurking in the fiber. So here's what happened. During the manufacturing of the first fiber optic cables, microscopic water impurities, these things called hydroxyl ions, would get trapped in the glass. And these ions were extremely thirsty for light at one specific wavelength, 1383 nanometers. They would just absorb it, creating this massive spike in signal loss known as the water peak. And this slide illustrates the solution just brilliantly.
The graph on the left, that shows that huge spike in signal loss. That's the water peak in the older fiber. But then, engineers developed new manufacturing processes to basically dehydrate the glass. And the result, on the right, is low water peak fiber, where that spike is dramatically reduced. That ghost was busted.
And the progress was incredibly fast. I mean, this chart compares fiber made in 1995 to fiber made just 5 years later in 2000. Look at that dramatic drop. Conquering the water peak was a huge deal. It opened up a brand new highway for data, enabling technologies that could send multiple signals down the same fiber at once.
All right, so we've got this amazing toolkit of different light wavelengths to find all sorts of problems. But that leads to maybe the biggest challenge of all. How do you test a fiber that's actively carrying all of our live internet traffic?
I mean, think about it. You can't just shut everything down to run a test. That would be absolute chaos. So technicians needed a way to perform this light-based radar while the fiber is in service, without disrupting a single bit of our data.
Well, it turns out there are two really clever ways to do this. The first is called in-band, and it's like finding an empty lane on the data highway and sending your test signal there. The second, and probably more common method, is out-of-band testing. This involves creating a brand new special lane just for testing, far, far away from all the regular traffic.
And here's how that out-of-band testing works. A special filter is put on the line that acts like an on-ramp on a highway. As this diagram shows, it merges a test signal, in this case at 1650 nanometers, onto the fiber right alongside all the live data. The equipment at the other end is totally blind to this specific wavelength, so the test signal does its job, gathering information completely undetected and without causing any interference. It's really genius.
So the big takeaway here is this. By understanding the unique properties of different wavelengths of light, how they lose power, how they spread out, how they react to stress, engineers have built an incredibly sophisticated diagnostic toolkit. It's this deep understanding of physics that keeps the invisible backbone of our digital world running smoothly every single day.
And that really brings us to the future, doesn't it? We've mastered this spectrum for today's needs, but as our demand for data continues to just explode, you have to wonder, what new properties of light will we need to unlock next? What new challenges will force us to find even more colors on this incredible, infinite highway of light?